Hey, I'm glad you're here. Come in, close the door on the day, and settle into a quieter room inside your mind. Tonight, we are not going anywhere fast. We will drift through the gentle side of the cosmos, where science speaks softly and wonder feels close enough to hold. Out there, stars are not just tiny lights. They are warm furnaces shaping the elements that became our oceans, our bones, and our breath. Their glow began long ago and has been traveling through the dark to reach you now. When you look up, you are reading time itself, one calm shimmer at a time. Let everything loosen. Unclench your jaw. Let your shoulders fall. Breathe in and let the exhale last a little longer than the inhale. If these quiet journeys help you rest, feel free to like and subscribe so we can meet here again whenever you need a peaceful night. No pressure, just an easy way back. For now, there is nothing you need to do. Let your thoughts grow lighter, like dust settling in a shaft of starlight. If you are ready, we will begin, letting the sky speak while your body remembers how to sleep. Take another easy breath. As your chest rises and falls, picture a single point of light growing larger, not because you are moving, but because we are letting our attention drift closer. The first thing the night wants to show you is scale. Some stars are so vast that the mind almost refuses to hold them. Astronomers give them names that sound like distant bells: UY Scuti, VY Canis Majoris, Betelgeuse. Their outer layers spill outward like slow tides of fire. If one of these giants were placed where our sun sits, its surface could swell past the path of Earth and keep going out toward Mars and even toward Jupiter. Numbers try to measure them and say something like more than 1,000 times the sun's radius, but the feeling of it is simpler. Imagine standing on a quiet shore and watching a red ocean rise until it fills the sky. Such enormity does not last forever. A giant lives quickly, as if size comes with a price. Where our sun will burn steadily for billions of years, these titans race through their fuel in only a few million. Their atmospheres are so puffed up that gravity struggles to hold them. Gas lifts away in curtains and plumes and begins to drift, and those drifts thicken into clouds that later glow as nebulae. From a distance, those clouds look like slow smoke, but inside them, the elements that will seed future worlds are being carried outward. To think of a star shedding itself into space can sound tragic, yet it is also generous. The material that leaves will one day become new stars, new planets, new air for new lungs. There is a quieter wonder in brightness too. Most stars shine with a steady patience, but a few live on the bright edge of what starlight can be. In the 1800s, a star called Eta Carinae erupted so fiercely that over a human lifetime, it became the second brightest star in our sky. It was not close by. It sits thousands of light years away. Yet, its outburst carved a glowing, double-lobed nebula we can still see in telescopes today. Astronomers also speak of quasars, which are the blazing hearts of distant galaxies powered by supermassive black holes. They are not stars, yet they help remind us that the universe can pour out more light than a person can imagine. When we say a single object can outshine a whole galaxy, we mean that space has rooms in it where energy gathers and sings at scales that are hard to hold in a single thought. You can let the grandeur wash over you without trying to pin it down. The sky is giving your mind permission to rest. From enormity and brightness, let us step softly into density. Picture a star that once was large, burning blue and white, finishing its life and collapsing. The core falls inward so far and so fast that the very structure of matter changes. Protons and electrons are pressed together until only neutrons remain. What is left is only about the size of a city, perhaps 20 kilometers across, yet it holds more mass than the Sunday. This is a neutron star, a kind of fossil left after a supernova. Still warm, still intense, but so compact that a teaspoon of its material would weigh as much as mountains. Its outer crust is a rigid lattice, below which lie layers of superfluid and superconducting matter that we cannot reproduce on Earth. Its gravity is an iron hand. If you could stand on such a surface, which you cannot, a jump would not carry you anywhere. Even light bends around it. Neutron stars are not silent. Many emit beams of radiation from their magnetic poles. As the star spins, those beams sweep across space like the beam from a lighthouse, and if Earth sits in the path, we hear a regular tick. Astronomers call these stars pulsars. Some rotate a few times a second, some far more quickly. The fastest, called millisecond pulsars, whirl hundreds of times every second, steadier than any metronome. Their timing is so stable that we use them as cosmic clocks, not because they are more precise than the best atomic standards we build on Earth, but because they hold their rhythm across vast distances and years. With networks of pulsars, scientists listen for the deep drum of gravitational waves, the long rolling swell that comes when massive objects move, and the fabric of space-time ripples. To imagine a clock that fits in your pocket is easy. To imagine one that lives in the sky, turning endlessly, is calming in a different way. There is order out there. There is patience. A few neutron stars are stranger still. In some, the magnetic field grows to almost impossible strength. These are magnetars, and their fields are so intense that they can twist the structure of atoms if you could bring them close enough. Sometimes those fields shift and snap. The star releases a flare that, for a heartbeat, shines brighter than everything around it. We have seen those flares from across the galaxy, and then the star fades back into its usual quiet. Magnetars are rare. None live near us, and that distance is a comfort. We can listen without fear, like hearing thunder echo beyond the far hills on a summer night. Now let your attention turn from density to motion. Not every star is a perfect sphere. A star that spins very fast, bulges at the equator, and flattens at the poles, shaped by its own rotation. Achernar is a famous example. Looked at closely, its equatorial diameter is about half again as large as its polar diameter. Spin can also fling gas outward into thin disks, and that gas glows and makes soft rings of light. When you look up with the naked eye, each star is a point, steady and simple. Up close they are dynamic, mixing their interiors, shifting their balance, living not as statues but as flames. Hypergiants feel like the culmination of all these traits. They are large, luminous, unstable, and short-lived. They push outward with such force that their outer layers cannot hold. Over thousands of years, they can shed amounts of mass comparable to the sun's entire mass, tossing shells and arcs into space. Eta Carinae sits in this category. The nebula around it is a memory of storms, dusty walls, and glowing folds of gas that were once part of the star itself. Hypergiants burn as if racing a clock. Their future is almost always a catastrophic supernova. Some will leave behind neutron stars. The most massive may collapse further and form black holes. To know this does not have to feel heavy. You can hold it as part of a cycle. What leaves is not lost. It becomes the raw material for whatever comes next. Black holes lead the mind to a different kind of quiet. They are not stars, though many are born from stars that were massive enough to fall beyond the neutron star stage. A black hole is a place where gravity is so strong that nothing, not even light, can escape once it is too close. Most of the time, a black hole does not announce itself. It waits. If a star wanders near and crosses a boundary where tides pull much harder on one side than the other, the star can be drawn out like taffy and then torn apart. Astronomers call this a tidal disruption event. The torn material swirls into a disk around the black hole, heats to millions of degrees, and shines in ultraviolet and X-rays. Sometimes narrow jets of particles shoot outward at nearly the speed of light. From Earth, we see a sudden flare at the center of a galaxy that slowly fades over months and years. It is a violent story, yet even here there is structure. The flare tells us the mass of the black hole. The way it dims tells us how matter falls. In the middle of destruction, there is a kind of clarity. Collisions tell clear stories as well. Imagine two neutron stars that were born in the same binary system, circling one another for ages as they lose energy to gravitational waves. Their orbits tighten. They circle faster. Finally, they touch and merge. In 2017, instruments on Earth felt the rise and fall of space-time from such a merger. Seconds later, telescopes saw a burst of gamma rays and then light across the spectrum. We learned that these collisions forge heavy elements like gold and platinum, mixing them into the universe. If you wear a ring, a part of it may have been made in the last moments of two dead stars spiraling together. There is something tender in that thought. Even the hardest events leave gentle traces we can carry. Stars do not always stay where they began. The galaxy is not a fixed stage. In some rare encounters, a star can be flung outward at such speed that it escapes its home galaxy entirely. We call them hypervelocity or intergalactic stars. A close pass by a supermassive black hole can provide the needed kick. The breakup of a dense cluster can too. Once ejected, that star will travel through the thin dark between galaxies, taking any planets with it if they survive the chaos. The image of a solitary sun moving through the deep is a quiet one. It does not blaze like a quasar or ring like a merger. It simply continues on, a small moving room of light with everything it needs bound to it by gravity. In that picture, there is both loneliness and calm. Drifting is not always a bad thing. Sometimes it is simply what happens when paths cross. You may notice that this tour has circled from large to bright, to dense to fast, to solitary, and yet the thread has felt even. That is because the night offers each scene like a tide offers waves. One flows into the next. The giant that sheds becomes the dust that cools. The dust that cools becomes the cloud where new stars form. The young star spins and flattens and throws off a ring. A ring may seed planets. Planets may bear oceans and eyes that one day look back and try to understand how it all came to be. A large star ends in a blaze and leaves a core like a stone, a neutron star that ticks. Two such stones find each other again and fall together, and something heavy and beautiful is made in the collision. Even a star that is torn to ribbons by a black hole leaves a light curve that teaches us nothing is wasted. Even endings in the sky are also beginnings. Some details add a gentle weight to that understanding. The light you see from Betelgeuse began its journey more than 600 years ago. The light from Eta Carinae has been coming for about 7,000. The shapes of their nebulae show the timing of winds and outbursts, one shell nesting within another, like tree rings. Acronar's flattening tells us how rotation competes with gravity. Magnetar flares tell us how magnetic fields store and release energy. Pulsar timing tells us that clocks exist in nature that keep time in their own quiet way. Gravitational waves tell us that space itself is not rigid, but supple, able to carry soundless music from events we cannot see with eyes alone. Each of these truths is a tool, but tonight they are also a lullaby. They reassure us that the universe has rules, and that those rules are elegant enough to sleep beside. Think again of the red supergiant that could envelop Earth's orbit. Think of the cloud of gas that flows away from it and later becomes part of a nebula. Inside that nebula, new stars will one day ignite. Around at least some of those stars, rings of dust will gather and sculpt themselves into planets. On one of those worlds, perhaps far in the future and very far away, someone may stand by a window at night and listen to a voice whisper about the sky. That thought is not science, yet it is aligned with it. Elements cycle, energy moves, information travels across generations and across light years. Your breathing is part of that rhythm. Inhale and let your shoulders float a little higher. Exhale and feel your weight sink deeper into the surface beneath you. We have walked past some edges without stopping to look down. There are subtleties inside each topic that we passed with a nod. The exact size of UY Scuti is still discussed, because measuring distant glowing spheres is not as simple as it sounds. Quasars are the cores of galaxies rather than stars, though their shine often tempts language to blur them together. Pulsars are stable in ways that make them perfect for some experiments, while laboratory clocks still lead in ultimate precision. Magnetars can, in theory, tear apart atomic structures, but only if you could approach them closely, which no person or spacecraft can. These clarifications are like small stones laid neatly at the edge of a garden path. They mark the borders so that the view remains wide but true. And now let us return to the feeling of it. Stars in all their forms make a kind of weather for the galaxy. Giant winds blow, gentle breezes of photons fall on dust and warm it. Storms erupt and fade. Lighthouses tick. Rivers of starlight flow along spiral arms. In that weather, our sun is a temperate day. It is unassuming compared to the giants and the exotic remnants we have visited, and that modesty is a blessing. Its steadiness gives us seasons and tides and time to learn. It is not the brightest or the largest or the strangest, yet it is perfect for a blue planet that wants to grow forests and stories. Keep your breath soft and even. Let the air move in and out, and picture the sky as it was before there were spirals, or bars, or neat city-like clusters of stars. In the young universe, the first lights began to kindle inside immense clouds of hydrogen and helium. Those clouds did not have heavy elements to cool them. Without that cooling, gas could not break into many small seeds. Instead, it gathered into a few enormous seeds that grew quickly. Astronomers call the first generation Population 3. We have not seen one directly, yet the story they tell is written into everything that came after. These first stars were likely many times heavier than our sun, some perhaps hundreds of times. They blazed with fierce heat and lived like bright matches, vivid and brief on cosmic scales. A few million years, then an ending that shook their neighborhoods. When they died, they exploded, and in those explosions, the universe made its first carbon, its first oxygen, its first iron. The darkness that came before was made of simple things. After these first stars, the air of the cosmos carried more notes in its song. Although none of those primordials survive today, their fingerprints remain. We read them in the chemical patterns of ancient stars that formed later, stars with extremely low amounts of heavy elements, yet still touched by that first enrichment. We read them in the faint glow that hangs over the universe, from a time when the first light ionized the fog and made space transparent. It is a quiet pleasure to imagine the moment when starlight first pierced the deep, as if the universe took its first true breath. What began as pure hydrogen and helium learned how to weave richer threads, and from those threads came galaxies, planets, oceans, bones, and the breath you are taking now. From the earliest giants, let us drift to endings of a gentler sort. Stars like our sun do not go out in one sudden beat. After a long main life, they swell into red giants, lift away their outer layers, and leave behind a core that glows with stored heat. We call that remnant a white dwarf. It is dense and small, about the size of Earth, yet it holds a mass comparable to the Sunday. At first it shines with a clean white light, not because of new fire, but because it is still hot from all the work it did before. Over very long spans of time, longer than any human story, and longer than the age of our universe so far, a white dwarf radiates its heat away. It cools, and as it cools, it dims, passing from white to blue, white to yellow to red, to a soft ember, and at last to something that no longer shines. That final quiet object is called a black dwarf. As far as we know, none exist yet. The universe is not old enough for even the oldest white dwarfs to have faded that far. The idea itself belongs to a far future when the sky has different colors and a different pace. It is a patient idea, and in thinking it, you may feel your shoulders drop a little more. When we talk about that far future, we step into the long, low notes of cosmology. If expansion continues and the universe keeps growing thinner, the rate of star birth will slow. The brightest and most massive stars will use their fuel and fade first. Stars like our sun will follow. The last to remain lit will be the smallest red dwarfs, those steady, thrifty fires. They will glow for trillions of years, longer than the universe has yet existed, and they will keep the darkness at bay long after the flashier lights have gone out. Imagine a night sky in that distant time. No bright blue giants, no summer triangles of vivid light. Instead, a dim sprinkling of cool red points spread thin across an ever larger vault. Some call this fate heat death, not because it is hot, but because energy is spread so evenly that no new work can be done. Galaxies grow faint, planets freeze, black holes endure. Then even they slowly release their energy over extraordinary periods. It sounds austere, yet there is peace in it. The universe has been loud in places. It has lifted great weights and rung with silent waves and built long chains of structure. In the far distance, it will rest. Not every story of the future is a single line to quiet. Some ideas in modern cosmology suggest that what we call the universe could be one chapter in a larger book. There are models where a previous cosmos contracts, bounces, and begins again. There are models where inflation, the rapid swelling that happened in our earliest moments, keeps happening in other places, spawning new regions with their own space and time. These are not settled truths. They are careful dreams, supported by math more than by direct sight. And scientists argue about their details with energy and goodwill. Yet, even to entertain them can be soothing. If there are other pages, starlight might begin again elsewhere, guided by the same laws, or by laws with different constants that still allow structure and warmth. The elements forged in one cycle could seed another. Renewal becomes not just a feature of stars that explode and enrich, but a rhythm that might echo on scales beyond a single universe. In that view, light does not end. It migrates. Come back now to stars that are alive today and to the ones that will make the far future gentle. Red dwarfs are the smallest and most common stars, the quiet citizens of the galaxy. They burn their hydrogen so slowly and so completely that they can shine for trillions of years without hurry. They are dim, invisible light. To your eyes under a dark sky, most will not appear at all. Through instruments they show steady faces and small flares, simple spectra, and a longevity that invites patience. Because they live so long, they offer an abundance of time for chemistry to explore paths toward life on any worlds that might circle them. The daylight on those worlds would be cooler and redder. The sunsets would be deep, wine-colored. We have not yet watched a red dwarf grow truly old. There has not been enough time. In the long seasons ahead, if you could look up, you would find that the galaxy's light is mostly theirs. If that far future sky seems sparse, remember that even a small light is generous in a dark room. As massive blue stars retire, as suns like ours take their turn, the red dwarfs will carry the torch. They will not be dramatic. They will not spray heavy elements into space by the ton. They will, very steadily, warm their planets and hold their systems together. Over time, they, too, will turn into white dwarfs and eventually into black dwarfs. The story slows from fireworks to embers. The idea of a cosmic twilight can sound lonely. It can also sound restful. A long evening with quiet lamps. Gravity will continue to shape the middle spaces, especially near the dense centers of galaxies. At the heart of the Milky Way sits a supermassive black hole known as Sagittarius A*. Around it, stars move in tight, elongated loops. One of them, S2, has been watched for decades. It sweeps in to a closest approach that is about 17 light hours from the center. In ordinary terms, that is roughly the width of our solar system. At that point in its path, S2 races at more than 5,000 kilometers per second. Its light shifts in color because gravity bends time and changes how we measure it. By tracing that path and others, astronomers have weighed the black hole and tested the predictions of general relativity. These are strong field laboratories, written in the language of orbits. They are also proof that stars can live surprisingly close to a place where the pull is absolute, as long as they keep to the right distance. The dance does not end at the edge of the shadows. It becomes more interesting. Encounters with black holes do not always lead in. Sometimes they lead out. If a star wanders near the deep well at a galaxy's core in the company of a partner, gravity can tear the pair apart. One star may be captured, while the other is thrown away with a fierce increase in speed. Such a star becomes a hypervelocity traveler. It can move fast enough to escape the galaxy's pull entirely, heading into intergalactic space. We have found several such runaways in the Milky Way. They probably began near Sagittarius A*, then took the long road outward. Picture, if you like, a compact solar system holding together under that acceleration. Any surviving planets feel the same tug and keep their orbits. The whole family moves through the thin dark between galaxies, a warm dot and a few colder dots under it, all bound to the parent light. There is a stark beauty in that scene, a house with its windows lit, drifting across a silent plain. While we travel across these ideas, you may notice that the tempo remains slow. The universe itself has fast moments, yet even its fast is patient compared to a heartbeat. Population. 3 stars are a flash compared to red dwarfs, but their flash lasts millions of years. The cooling of white dwarfs to black dwarfs lasts far longer than all of human history combined. The long fade into a quiet cosmos lies at distances our minds cannot truly grasp, which frees your mind from trying. You can allow the numbers to turn into images. First light blooming in a fog, a white coal that glows and then rests, a deep red lamp that stays lit through 1,000 nights, a star looping close to a dark center, like a swallow skimming a well, a lone sun crossing a space so empty that it hums. Small clarifications, kept gentle, help the picture stay true. The first stars were likely massive because low metal content meant less cooling and fewer fragments. We infer their existence from the chemistry of later stars and from the background light left by reionization. White dwarfs cool because they have no new fusion and slowly radiate energy from their hot interiors. Black dwarfs are predictions that follow from that process, not observations we can make yet. The heat death picture depends on continued expansion and on the laws of thermodynamics. And there are other endings proposed in the literature, including those bounces and births we touched on earlier. Red dwarfs are good at making the most of their fuel, yet their planets must also deal with stellar flares and tides, and those details are active fields of study. S2 and its kin mark out the mass of Sagittarius A times with a confidence that grows with every orbit we record. Hypervelocity stars are rare, but they exist, and their paths teach us about the gravitational heart of the Milky Way. Each of these nodes is a small lamp in the room. Together, they make a soft light you can rest in. The universe has been breathing in its own way since the first stars. It inhales when gas cools and sinks into new wells of gravity. It exhales when stars push outward with light and wind. The first generation took a sharp breath inward and lit. Their endings were like a long exhale that carried new elements into the open. Later generations did the same on smaller scales, always mixing, always moving material from one form to another. In your body, oxygen rides on iron in your blood. The iron came from a star that died. The oxygen came from a star that lived brightly and shared. Things that seem far away are already near. The past travels with you. The far future will travel with someone else. Perhaps not a someone. Perhaps only clouds and stones and black dwarfs cooling in a quiet night. Yet even in that quiet, the trace of what happened remains. The universe keeps its records. We read them in light that left long ago and in the slow gravity-drawn shapes of orbits. We read them in the faint chemistry of old stars and in the red points that will keep the night soft when most lights are gone. None of this asks anything urgent from you. It invites you to lie back and let the images rise like constellations not in the sky, but in your own thoughts. If your breathing has found a slower rhythm, let it continue. The first stars ignite again in your inner eye, then fade and leave gifts behind. White dwarfs cool, not tonight, but over ages so long they feel like stillness. Red dwarfs keep the lamps lit. A star sweeps around the center of the galaxy and does not fall. Another takes flight and heads for the open. The future tilts toward quiet, and nothing about that quiet is unfriendly. It is simply the long rest that follows a great work. The sky above you is still in its bright age. You are alive while galaxies sparkle and while suns of many colors fill the dark with detail. That is enough for now. Let the breath you just took carry you a little farther. When you look up and see a single point of light, it often hides a quiet partnership. Many stars live in pairs or in small families, held together by gravity. They turn around a shared center, the way skaters circle an invisible mark on the ice. Some partners keep a respectful distance and take thousands of years to complete a loop. Others drift so near that one star can pull gas from the other, and the shared material forms a delicate bridge between them. Our nearest stellar neighbors, the Alpha Centauri system, are a trio, And from a world orbiting there, the sky would sometimes have more than one sunrise. Multiple shadows would stretch across a landscape, then slide back together as the suns glide down. These hidden families are more than curiosities. They tell us how stars are born. Clouds of gas often fragment into more than one seed, which is why binaries are so common. By watching how pairs tug on each other, astronomers learn their masses and ages, and from those clues, they learn how stars grow. What appears as a solitary lamp to the eye is often a long, slow waltz. The steps of that waltz do not end with a final bow. The death of one star often sets the stage for others to arrive. When a massive star reaches the end of its fuel and collapses, the outer layers rush outward as a supernova. That wave of pressure moves into the cooler spaces around it and squeezes nearby clouds, where the cloud was just shy of being able to fall in on itself. The push is enough to begin the collapse. The result is fresh star birth. Our own sun may have begun its life in a place touched by such an event, with the nursery enriched by the heavy elements from an earlier generation. In this way, endings carry beginnings inside them. A single bright life can leave behind a whole cluster of new lights. Even among endings, there are variations that keep the sky interesting. Some very massive stars sit in a tricky region of physics, where the heat in their cores creates pairs of electrons and their antiparticles. That change steals pressure that had been helping hold the star up. The star contracts and heats, then throws off a huge shell of gas, and for a time it survives. Years or decades later, it can repeat the outburst. Eventually, stability fails and the star collapses for good. Astronomers call this sequence pulsational pair instability. From a distance, the repeated flares can look like a star that will not let go. It brightens, rests, and brightens again until gravity has the final word. These rare stories remind us that stars live on a spectrum of behaviors, and that the line between life and death can be a borderland rather than a single cliff. Not all explosions come from stars that still fuse elements in their cores. In some cases, the star is already a compact ember. Imagine a white dwarf, the hot core left after a star, like our sun, has shed its outer layers. If that white dwarf has a companion and slowly gathers matter from it, the extra weight can push the dwarf to a critical point. The star cannot support itself in the same way anymore, and a runaway thermonuclear fire races through it. The result is a type Ia supernova. These events reach nearly the same peak brightness because they begin at nearly the same mass. They are not perfect copies, yet their light curves can be corrected in a reliable way. This makes them excellent distance markers. By measuring how bright they appear and knowing how bright they truly are, astronomers can learn how far away they sit. 2 decades ago, such measurements across vast stretches of space revealed that distant supernovae were dimmer than expected. The simple answer was distance, but the deeper answer was that the universe is not just expanding, it is expanding faster and faster. Something we call dark energy seems to be driving that acceleration. In this sense, the quiet cinders of old stars helped us weigh the size and mood of the cosmos. The material those explosions scatter tells another, more intimate story. Heavy elements are forged in stellar cores, and in the violent moments when stars die, iron and calcium were cooked under pressure. Carbon and oxygen were assembled atom by atom in hot interiors. Gold can be made in the richest fireworks of the universe, including some supernovae, and in the mergers of neutron stars. When the shock fronts move outward, the elements ride along and mix into the thin gas between stars. Over time, that gas coalesces into new systems. The iron in your blood once lived in a star. The calcium in your bones once crossed interstellar space. The oxygen you breathe was released by long-gone suns. People often say we are made of stardust because it is true in the most literal sense. The connection is not only poetic, it is chemical and physical, and present every time you inhale. If the sky is a place of invention, there is also a quiet threshold that marks the last chapter for a massive star. Fusion is the engine that keeps a star shining. Light elements combine into heavier ones, and the energy released holds up the weight of the star against gravity. This trade works beautifully for hydrogen and helium and continues through carbon, neon, oxygen, and silicon. When the core begins to build iron, the bargain fails. Fusing iron does not pay back energy. Instead, it costs energy. The moment a core becomes rich in iron, the star runs out of tools to hold itself up. Gravity wins. The core collapses in a breath. The outer layers fall in, bounce, and blast outward. What happens next can produce a neutron star or a black hole. The quiet metal in a nail, the metal in a red planet's dusty soil, points to a pivot in a star's life when the light could no longer be fed from within. Return to the groupings again and see how all of this weaves together in a close binary. The more massive star usually evolves first. It swells, and as it does, gas can overflow from its surface toward its partner. The transfer can change both lives. The less massive star eats and grows, the more massive star thins and changes course. Later, the white dwarf that remains may siphon material back and ignite as a Type Ia supernova. A single pair can host many stages of the stellar cycle if given time. Farther out pairs keep their distance and age more slowly. Their gravity still matters. It shapes any planets they host, carving neat orbits or eccentric paths. From the surface of one of these worlds, the light would come in layers, warm and red from one sun, clean and white from another, and the clock in the sky would have more than one hand. The debris from every major event drifts outward to be used again. A supernova shell expands and thins. Within and around it, small knots contract into new stars. Those stars often belong to associations or clusters, born together and moving together like a school of fish, then slowly dispersing as they age. In some of those clusters, a single very massive star is troubled by pair instability and stages a series of dramatic outbursts before its end. In others, a quiet dwarf takes on just enough mass from its neighbor to light the kind of supernova that serves as a beacon for measuring the universe. Meanwhile, far away from these busy regions, an old binary in the halo of a galaxy keeps its long appointment, swinging once every few thousand years, shining too faintly for naked eyes, but precisely enough for careful instruments. Every time you hear the word supernova, you can think maker as well as destroyer. Without such explosions, there would be few elements heavier than helium. Without those elements, there would be no rocks, no rivers, no people to wonder. The same is true for the softer processes of stellar winds. Hypergiants shed layers even before they die, and those winds carry out carbon and nitrogen and other building blocks. The galaxy is constantly enriched by both violent and gentle means. Consider for a moment how these processes look, written across time. A cloud fragments and forms a few stars at once. Some of those stars are paired. One of the pair goes through its fuel quickly and swells, then transfers mass. A close relationship pulls matter into a disk that glows. The heavier star ends its life, and the very shock of that ending gathers the surrounding gas and wakes new lights. Among those newborns are some small red dwarfs that will shine steadily for trillions of years. Among them may be a star, like our Sunday. Around a few of those stars, planets take shape in rings of dust, and on one of those planets, chemistry learns to fold into memory. One day, someone on that world looks up and notices that what seems single is often double, that the sky is stitched together by quiet bonds. There is humility in the thought that iron, so ordinary and useful here, marks the limit of stellar endurance. When iron builds up, support fails, and the star's heart collapses. That collapse is not the end of meaning. The outburst that follows writes information into the surrounding space. It plants elements where none existed before. In that mix, it pushes on cold gas and starts a new chapter. Even the leftover compact core, a neutron star, or a black hole, affects its neighborhood. It can pull on a companion and turn their shared life into an X-ray beacon. It can set the conditions for future fireworks. It can simply sit in the dark as a heavy reminder of what light can become. All of this feels grand, yet for a listening body at rest, these are small motions, two dots circling, a wave moving through a cloud and tightening it just enough, a slow drift of ash becoming soil. The light curve of a type Ia supernova, rising and falling like a measured breath. The idea of iron forming in the last moments before a star gives way. Each picture is a step that carries you into a calmer place. The science is firm where it needs to be, and gentle where mysteries remain. And in that balance, your mind can loosen its grip. So, when you watch a single star glitter, you can keep in mind the possibility of a partner you cannot see. When you hear that a faraway spot suddenly brightened and then faded, you can imagine the reasons. Without worry, a dwarf may have crossed its threshold. A rare giant may have coughed and then settled before its final sleep. Somewhere, a shock wave may be pressing a cloud into the next generation. Somewhere, a core may be crossing the iron line and preparing to hand its light back to the room. Let the next breath arrive. Picture the sky as a quiet workshop where matter is traded, reheated, and offered forward. Picture the slow dance of pairs, the gift of heavy elements, the measured lamps that help us gauge distance, and the simple fact that the iron in your blood remembers a furnace hotter than anything we can build. What seems remote is already within you. What seems final often hides a door. The stars do not simply end, they pass the torch. And while they do, they teach us to rest inside long stories without needing to rush to the last page. The stars we have been visiting are not only storytellers, they are tightrope walkers. Every sun holds its shape by keeping two great forces in quiet conversation. Gravity gathers the star inward, tugging on every atom. From the center, heat and light flow outward from fusion, where hydrogen becomes helium and the small bit of mass becomes energy. Warm gas pushes back against weight, and for a long while the whole sphere rests in balance. If the outward push strengthens, the star swells until pressure eases. If it weakens, the star contracts. The core warms, and support returns. For billions of years, our sun has kept that steady rhythm. It shines because fusion lights it from within, and it survives as a star because that light holds gravity in check. This balance explains why stars do not collapse in an instant or blow apart the moment they ignite. Imagine a giant cloud of gas with no fusion at its core. Gravity would compress it fast, heating the center, and without a counterforce, the collapse would run away into a compact remnant. Fusion stops that slide. Energy moves outward. Each layer supports the one above, and a calm lamp appears in the dark. Even the sun, with its friendly golden glow, lives on a fine edge. Heavier stars stand on sharper edges. Their cores run hotter, their atmospheres churn harder, and their lives pass more quickly. Mass sets the tempo. The most massive stars pour through their fuel at astonishing rates. Stronger gravity compresses their cores. Higher temperatures drive fusion far faster, and the result is fierce blue light and powerful winds. These giants carve hollows in nearby clouds, and the edges of those hollows glow, yet their brilliance is brief. Where the sun needs about 10 billion years to finish its core hydrogen, some blue giants race through that chapter. In only a few million, they end violently, often with supernovae that enrich their neighborhoods with heavy elements. Think of the galaxy as a city of lamps. Small red lights stay on all night. Bright blue lights blaze early and vanish before midnight. Each has a role. The steady ones keep time. The brilliant ones reshape the room and give it new materials when they leave. Our own sun will change too, though not soon. In roughly 5 billion years, the core hydrogen will be spent. Fusion will shift to a shell around the core, while the core itself contracts and heats. The outer layers will respond by expanding and cooling. The sun will grow into a red giant, a vast, ruddy lantern with a surface far beyond its current reach. Mercury and Venus will be lost. Earth may be swallowed or stripped. The light will turn deeper and softer, the atmosphere more extended. After this phase, the outer layers will drift away as a thin, glowing shell, a planetary nebula you could trace with a fingertip if you were close. In the center, a white dwarf the size of Earth will remain, dense and hot, shining with stored heat for a long time before it cools. None of this asks for worry. The timescales are so long they feel like a dream, seen from far away. The lesson is rhythm. Gravity and fusion take turns leading, and the dance writes the future. You can see that balance play out in a familiar light. On a clear evening, Sirius looks like a cold spark, almost electric. It dominates because it is luminous and close by, only about 8.5 light years away. Ancient eyes noticed it early and tied it to calendars and travel. Egyptians watched its dawn rising as a sign of the Nile flood. To a modern observer, Sirius is also a reminder that single points can hide layered stories. It is not one star, but two, bound together. Sirius A is the bright primary. Sirius B is a faint white dwarf, the dense ember of a star that once shone as we do now. The pair orbits a shared center and blends to the naked eye into one blade of light. The past and present of stellar life sit side by side in that one place. Names rest on the sky like soft anchors. Long before catalogs and coordinates, people named the lights they trusted: Betelgeuse and Rigel in Orion, Aldebaran in Taurus, Vega in Lyra, Altair in Aquila. Many names carry Arabic roots that traveled through Latin into modern charts. Other traditions in China, India, and across the Pacific kept their own star names alive in poems, calendars, and songs. The permanence of those sounds gives a human texture to the night. Astronomers use precise designations for work, yet the old words remain like heirlooms. The science explains how stars live. The names remind us we have watched and spoken of them for a very long time. Those names were also tools. Navigators once crossed oceans by keeping star paths in memory. Polynesian wayfinders read the rising and setting points of stars, the feel of swells, and the pattern of winds to cross thousands of kilometers of open sea. In the north, the star we call Polaris hangs close to the spin axis of Earth. Its height above the horizon reveals latitude, and its fixity gives a steady reference point. Traders in the Arabian Sea, pilots in the Mediterranean, and Viking crews in the North Atlantic all used starlight to find their way. Seasonal migrations on land were timed by star risings as well. The techniques were passed by story and song, whole charts encoded in memory. Navigation by the sky required clear nights, careful practice, and trust. It worked. Even the pole star changes. Earth's axis slowly traces a wide circle through the sky over about 26,000 years, a motion called precession. Because of that wobble, the point near true north drifts among the stars. Around 3000 BCE, a dim light in Draco named Thuban stood close to the pole. In about 12,000 years, the bright star Vega will take the role. Polaris is simply the current caretaker. Stone circles and pyramids aligned to the heavens did not always point to the same markers we use today. Thinking about that change feels like watching Earth breathe across millennia, a slow inhale and exhale that redraws the sky's compass over ages. Perspective changes patterns too. Constellations are pictures we draw by connecting bright points that only line up from here. Move a few dozen light years and the drawing breaks. Lines bend, shapes fade, new shapes form. Stand on a planet near Proxima Centauri, and our sun would join their sky as a modest extra star. From a world in Andromeda, The Milky Way would be a river of light, and our familiar figures would dissolve into its glow. The night is not a flat map, it is a deep ocean. Every shore offers a different arrangement. To imagine other skies is to practice humility. Our constellations are local art, useful and beautiful, but not permanent. Time changes those drawings. Stars creep across the sky relative to each other at a speed too slow for casual eyes. Yet over thousands and millions of years, the change matters. Orion's belt will not always be a neat row. The Big Dipper will stretch and twist into something unrecognizable. Clusters will spread. Associations will dissolve. New groupings will invite new stories. This does not lessen what we see now. It gives the sky a living quality. The figures we love are snapshots in a long film. Future watchers will inherit different maps and make myths of their own. Return to the engine beneath all these scenes. In stellar cores, fusion turns light elements into heavier ones and releases energy. In small stars, hydrogen becomes helium slowly and steadily. In larger stars, after hydrogen is gone in the core, helium fuses into carbon and oxygen. In the largest, the sequence speeds up, stacking layers that burn different fuels at once until the core builds iron. Up to that point, fusion helps hold the star up because it releases energy. Iron changes the terms. Fusing iron does not pay back energy. It costs energy. When iron accumulates in a massive core, support fails. Gravity wins. The core collapses in a heartbeat. The outer layers fall inward, rebound, and a shockwave races outward. Neutrinos rush through everything. Light follows. For a brief time, a new jewel appears in the sky and then fades. A neutron star or black hole remains. Elements disperse and seed the next generation. Support, loss, release, renewal. A breath in the language of stars. The balance that holds a star is mirrored in the quieter details on its surface. Our sun's face swirls with convection cells the size of continents. Arches of magnetism rise and snap, throwing off flares and clouds of charged particles that take days to sweep past Earth and light the polar skies. None of that surface weather disturbs the deep equilibrium that keeps the sun intact. The core continues its careful work while the skin dances. In heavier stars, the weather is wilder. In lighter stars, the flares can be frequent. Yet the principle holds. Fusion supplies pressure. Pressure supports weight. The star endures until its fuel and physics say otherwise. Let Sirius stand as a small mirror of all these layers. The bright primary holds its balance today. The faint partner has finished its main fuel and rests as a white dwarf. The pair was born from a cloud enriched by older explosions. Its ancient names carry the footprints of navigators and storytellers who trusted the sky. The light you see left years ago to find you now. The constellation around it will distort into a new figure for someone far in the future. In one point of light, there is structure, history, and motion across many scales at once. Let your attention rest on the simple idea that light does not always travel in straight lines. Space has weight, and where matter gathers, space itself curves. When a distant star's light passes near a massive object, the path bends and sometimes splits. Astronomers call this gravitational lensing. In gentle cases, the bend is slight, like a clear stream easing around a stone. In stronger cases, the light is magnified, copied into multiple images, or stretched into thin arcs. On rare, near perfect alignments, a single faraway star brightens for a short time and becomes visible across billions of light years. Without this natural magnifier, we would never have seen it. Lensing changes how we think about distance and structure. Space is not an empty scaffold. It is flexible, and gravity leaves marks on every beam that crosses it. By tracing tiny distortions, scientists can map the mass that causes the bend, even when that mass is dark and unseen. Entire clusters of galaxies act as lenses, revealing still more distant galaxies behind them. Closer to home, microlensing is like a whisper that swells the light of a background star when a compact object drifts in front. The brightening fades again, but the brief swell can betray a hidden planet or a dim companion. Even starlight learns from gravity as it travels. Patterns change too. Constellations are pictures we draw by connecting bright points that happen to line up from here. They have guided travel and stories for thousands of years, but they are not fixed. Stars move with their own slow paces around the galaxy, and over long spans those motions redraw the figures. Orion will loosen, the Big Dipper will stretch and tilt until the cup is gone. New patterns will appear and wait for new stories. Our maps are true for our century, not for all time, and that is part of their charm. They mark the sky we share, the way old sea charts mark waters once thought endless. Even within a human lifetime, the sky is not perfectly still. Proper motion is a star's slow slide against the background. The distances are so large that most slides are too small to notice without careful instruments. Yet a few lights reveal their motion over decades. Barnard's star is the classic example. It creeps across its patch of sky faster than any other star we can see from Earth. A quiet reminder that suns are not pins in a dome. They are travelers with their own directions and speeds, and our eyes are simply too brief to follow them far. The sun is moving as well. Our star orbits the Milky Way's center in a few 100 million years, riding with a stream of neighbors through a spiral arm. As we go, the local roster changes. The stars that appear close to us now will drift away, and others will take their places. Long ago, a different set stood near. Far ahead, another set will. When we look up, we are seeing a single frame in a long journey. The companions around our sun come and go, and the sky of a distant epoch would be familiar and strange at once. There are places where time seems to gather and hold. Globular clusters are ancient, rounded swarms that orbit the outskirts of galaxies. Each one holds hundreds of thousands of stars packed into a small volume, like a fistful of frost crystals thrown into the night. The centers are so crowded that the stars begin to blur together in a telescope's view. Many clusters in the Milky Way are more than 12 billion years old. Their massive stars burned out long ago. What remains is a population of small, long-lived suns and red giants shining steadily after almost the entire history of the universe. By studying their ages and compositions, astronomers read a chapter from the time when the galaxy was young and still learning how to assemble itself. Not all elders live in tight gatherings. Hidden among younger populations are rare, ancient stars that formed soon after the first generation. They were made from gas with very few heavy elements. Their light carries a sparse chemical fingerprint, almost untouched since the early universe. Finding one is like discovering a pressed leaf between the pages of a very old book. It is fragile, and it holds a memory of another season. These survivors offer clues about how quickly the first stars seeded their neighborhoods with heavier elements and how the earliest structures came together. To look at one is to look toward a time when the cosmos was just beginning to sparkle. Galaxies themselves do not keep still. They approach, pass through, and sometimes merge, turning two great swirls of stars into one larger system. Through all of this, many individual stars keep shining as if nothing had happened. A sun born in a small satellite can be swept into a bigger spiral and live on for billions of years in its new home. Some are thrown into the space between galaxies, wandering in the thin dark that stretches from cluster to cluster. These are solitary witnesses. They outlast the shapes that first gathered them and carry their light beyond the boundaries where they were made. All of these motions and mirrors are gentle to the ear. Gravitational lensing is simply gravity curving light. Proper motion is simply travel seen from far away. Globular clusters remain because they formed early and held together. Ancient, chemically simple stars exist because not everything has mixed. Stars outlive their galaxy's outlines because a sun's fuse can burn through upheaval without noticing. Each idea is a small key. Together they open a view of a living sky. If you could rise above the galactic plane and look back, you would see our neighborhood swimming slowly through the Milky Way's glow. The sun would be one bright speck among many, tugged by the same gravity that pulls whole streams of stars. Farther out, the globular clusters would trace a loose halo, their cores sparkling like grains of salt in a dark hand. Beyond them, a distant galaxy might shine through the lensing field of a cluster between us and it, its light arcing where mass has curved space. Somewhere nearby, a very old star would carry a simple spectrum, the imprint of a time when the periodic table was sparse. Somewhere else, a runaway star would be on a long road between galaxies, patient and solitary. To look up now is to catch the sky mid-motion. Light bends, patterns shift, neighbors come and go. Old swarms circle at the edge of our vision, and a few elders glow with the same faint chemistry they have worn since almost the beginning. None of it is hurried. The changes are grand and slow, a graceful rearrangement that lets the mind rest while the universe keeps time. Some stars wear their history on the outside. Around them hang thin shells and ripples of gas and dust, thrown off during restless moments and softly lit by the star within. Seen through a telescope, the shapes become rings, arcs, and bubbles, as if a stone had been dropped into a still pond of space and the waves froze into light. The reasons are varied. A star can lose mass in a steady wind, layer by layer, year after year. It can also swell and briefly erupt, shedding part of its outer skin in a single breath. When the breeze is strong, the shells grow and drift. When the wind falters, the shells overlap like tree rings, marking separate episodes of change. What first looks decorative turns out to be part of a deep exchange. Those veils carry carbon, nitrogen, oxygen, and heavier atoms outward, where they can cool, gather, and someday take part in new stars and planets. Among the most dramatic sources of these outflows are Wolf-Rayet stars. They are rare, massive, and stripped down by their own intensity. Their surfaces are so hot that their outer layers cannot hold on. Gas lifts away in fierce winds, and the star is left with its inner parts exposed, glowing with a heat that can exceed 50,000 degrees Celsius. Spectra from these stars show strong lines of helium and heavier elements, a sign that we are seeing deeper than usual into a stellar interior. The winds can remove mass at a rate that would empty Earth many times over in a single year. Around some Wolf-Rayet stars, the expelled material piles into bright, textured shells and arcs that spread for light years. The stage does not last long. After this brief, powerful chapter, many of these stars end in supernovae or collapse into black holes. They live short lives, but they give generously to their surroundings. A moving star can carve a different kind of shape. When a sun plows through interstellar gas at high speed, it pushes the medium into a curved front that glows in infrared light. Astronomers call the result a bow shock, and the analogy to a boat's wake is exact. The shock marks both the direction of the star's travel and the density of the material it is crossing. The arc persists only while the star moves through gas that is thick enough to feel the shove. Then it fades. Along certain lines of sight, you can see the star and the glowing crescent ahead of it, a frozen wave announcing that this traveler is not at rest. Some of these fast movers are runaway stars. They begin in clusters, where close encounters are common, or near massive partners that end in supernova explosions. A strong tug or a sudden kick can fling a star outward at hundreds of kilometers per second. The fastest reach, escape speed, and leave the galaxy behind. If planets share the star's motion and remain bound, they cross the void together as a small fleet, a warm lantern and any surviving worlds circling it, far from the lights of a city of stars. It is a stark picture, but not an unfriendly one. The universe leaves room for quiet travelers. The youngest suns do not advertise themselves at first. They are born inside cold clouds, where dust grains block visible light. In those places, ordinary telescopes see only darkness. Switch to infrared or radio, and a hidden nursery appears. Cores collapse into compact knots called protostars. Around many of them, flat disks of gas and dust gather and slowly sort themselves into rings. From the poles of the forming star, narrow jets shoot outward, carving channels through the cloud and lighting it from within. In images, the jets look like thin beams, and the places where they strike denser pockets glow as little knots called Herbig-Haro objects. The entire scene is slow-motion craft. Gas falls in. Some is spun into a disk. Some is launched out in jets that carry away extra angular momentum. When the core temperature reaches roughly 10 million degrees Celsius, hydrogen fusion begins. Only then does a protostar become a star in the full sense and join the main sequence of stellar life. Before that ignition, a protostar shines using a different fuel. Gravity does the work. As the gas falls inward, It releases potential energy as heat. That warmth leaks out as faint light, giving the object a soft glow that does not rely on nuclear fire. This prelude can last hundreds of thousands of years. In that time, pebbles in the disk stick together, grow into boulders, and begin the long path toward planets. The scene is muffled and private, hidden by dust until winds and radiation clear the cocoon. Not every object formed in a cloud becomes a true star. Brown dwarfs inhabit the space between the largest planets and the smallest stars. They are too massive to be planets as we usually define them, but not massive enough to sustain steady hydrogen fusion. Some can briefly fuse deuterium, a heavy form of hydrogen, when they are young and hot. Then they cool and dim, shining mostly in infrared. They can drift alone or circle other stars, and they come in a range of sizes that challenges neat categories. Call them failed stars if you like, or overgrown planets, but it may be more accurate to see them as their own class, a reminder that nature prefers spectrums to sharp borders. Stellar lives also intersect in more direct ways. When two stars orbit closely, they can lose energy to tides and shared envelopes and slowly spiral together. If they merge, the event releases a burst of light and throws off material in a glowing shroud. The new star that forms is often larger, hotter, and more unstable than either parent was. In crowded clusters, such mergers can create blue stragglers, stars that look younger and bluer than their neighbors of the same age, as if they had been rejuvenated. After a merger, leftover gas may settle into a disk. In some cases, that material can feed new structures. In others, it disperses into the cluster as raw ingredients to be used elsewhere. Even when two stars remain separate, they can still alter one another's paths. In a binary, the more massive star usually evolves faster. When it swells into a giant, its outer layers can spill over a boundary called the Roche lobe onto the companion. Mass transfer transforms both. The donor thins and can be stripped down to its core, which may later cool into a white dwarf. The accretor grows and can spin up, heating and brightening under the extra fuel. In extreme cases, the flow drives outbursts. A white dwarf that gathers too much gas can flare as a nova, brightening and then fading as the layer on its surface ignites and blows away. If the white dwarf approaches a critical mass, the entire star can ignite in a runaway fire and become a type Ia supernova, a standard candle that helps us measure the size and history of the universe. Quiet theft and bright fireworks are different chapters of the same partnership. Add a third star, and the geometry becomes more intricate. Some triple systems are hierarchical, with a close pair and a distant third that orbits the pair. Others are more balanced and less stable. Gravitational nudges in such systems can tilt or stretch orbits, slowly pumping eccentricity until paths cross or until a planet's seasons become extreme. A world under 3 suns would see a sky with strange rhythms. Daylight could rise from one horizon, while another sun sets on the opposite side. Shadows would multiply and slide in patterns that repeat only over long intervals. Triples are not rare. They show that variety is one of the universe's most reliable habits. All of these scenes fold back into the larger cycle. Shells and winds carry heavy elements into the interstellar medium. Bow shocks and runaways trace motion through that medium. Protostars assemble quietly, then switch on. Brown dwarfs remind us that thresholds have widths. Mergers reset clocks for some stars and change the balance in clusters. Mass transfer and triples reshape orbits and fates in ways that keep astronomers alert and curious. None of it is frantic. The processes play out on scales that invite patience. You can hold the images lightly and let them settle. Picture an old star wearing thin veils that mark past storms. Picture a stripped, bright Wolf-Rayet core blowing a constant gale. Picture a fast traveler with a faint crescent before it, where gas is being pressed and warmed. Picture a newborn sun, hidden in a dusty cradle, with narrow jets chiseling paths to daylight. Picture a quiet brown dwarf, fading into the infrared, small and steady beside a brighter neighbor. Picture two stars circling until they fold into one and briefly flare. Picture a swollen giant pouring gas onto a partner, its glow rising and falling as the flow surges. Picture three suns locked in a slow, elegant dance that complicates every orbit nearby. Each picture sits comfortably beside the next, part of a single fabric. The through line is simple. Stars are not isolated points. They are actors in a medium, shaped by it and shaping it in return. They breathe out and in. They brush past. They pair up. They grow. They shed. They merge. They pass material. They raise the lights and lower them again. Gas remembers their moods in rings and arcs. Dust keeps their secrets until it is ready to reveal a new generation. The galaxy keeps the score in clusters and streams and halos that drift on while the details change within. Hold the idea that all of this is happening above you, unhurried and exact. Hold the idea that the elements in your body once passed through those veils and winds. Hold the idea that somewhere, right now, a star is putting on a new shell of light while another takes one off. Some worlds do not wake to a single sunrise. Planets can move around two suns at once, circling a close pair, the way a moth traces a lamp's edge. Astronomers call those paths circumbinary orbits, and we have watched their signatures in the light of distant systems. Kepler taught us that science fiction skies with twin sunsets belong to real places. Daylight on such a world would come in blends and layers. Shadows would double and slide apart, then knit together again as the stars crossed the sky. Temperatures and seasons would follow patterns less tidy than Earth's, yet still orderly enough for stability over long spans. Other planets keep to one star in a binary and treat the partner as a brilliant second lantern. From that ground, the companion would rise and set like an oversized moon, sometimes near, sometimes far, changing pace as the two suns moved through their dance. Life, if it found a foothold on such a world, would learn calendars that braid two cycles together. Dawn would not always mean the same color. Evening would not always fall the same way. These arrangements widen our sense of what a stable home can be and remind us that nature writes more types of sky than we imagined. Many suns begin life in company. Clusters are the nurseries, where gravity gathers gas into a burst of stars and then binds the new family for a while. In a telescope, a rich cluster looks like a handful of glitter tossed into the dark. The closest members are crisp points. The center becomes a soft frost of light where the stars crowd together. In the densest clusters, the distance from one star to the next can be a fraction of a light year, far closer than in our quiet neighborhood. Encounters are common there. Systems trade partners, orbits tilt. Some planets are nudged into new paths. Others hold on and learn to live with a busier sky. There are two broad flavors you can hold in mind. Open clusters are young, loose gatherings. They carry many hot blue stars that shout their youth with strong light and strong winds. The Pleiades are a famous example. Open clusters do not last. As they orbit the galaxy, tides and passing clouds tug them apart. Over hundreds of millions of years, they dissolve, their members drifting outward to become ordinary field stars in the galactic disk. Our sun likely began among such siblings long ago and then wandered off when the family dispersed. Globular clusters are older and tighter. They are near spherical swarms that orbit the galaxy's halo, like distant lanterns, each one holding hundreds of thousands of stars bound by their collective gravity. Many are more than 10 billion years old, nearly as ancient as the Milky Way itself. Their brightest massive stars died early. What remains is a steady population of red giants and long-lived dwarfs, shining with the patience of age. To look into a globular's heart is to see crowding so thick that the eye blends the points into a granular glow. Their endurance makes them valuable records. By reading the colors and compositions of their stars, astronomers piece together conditions from the time when the galaxy was still assembling. Clusters do not lie to us about time. Open groups fade away and leave no obvious trace. Globulars persist and carry the memory of the early universe around the galaxy like keepsakes. Both teach the same lesson. Stars are born together more often than not, then go their separate ways. Some carry planets with them. Some end as dense remnants that keep pace with their old neighbors for eons. A cluster is a community in motion, and motion is part of the story from the beginning. Not all galaxies keep a slow pace. While this happens, some experience hurried seasons of starbirth. In a starburst, clouds collapse across wide regions, and new clusters form at rates far above the quiet background of a normal spiral like ours. Tidal forces in a close encounter or a merger can compress gas and spark these events. For a short while, by cosmic standards, tens of millions of years, the galaxy blazes with newborn light. Winds from massive young stars and from supernovae carve bubbles. Dust glows in infrared maps. Then the gas thins, the fireworks fade, and the system returns to a calmer rhythm. Starbursts show that the universe breathes in many tempos. Some places keep a steady pulse. Others sprint and rest. The rooms where stars begin are larger than the single points they eventually become. Giant molecular clouds can span hundreds of light years, cold and dark, invisible light, yet rich in material. Within them, small knots collapse under their own weight. As they do, they warm and begin to shine in infrared. The Orion Nebula is a nearby window into this process. Through binoculars, it is a faint haze, Through a larger instrument, it becomes a cavern of light, with young stars hollowing out a space in the cloud and illuminating the walls. In such places, entire generations form together, some large and fast, some small and long-lived, some in pairs, some alone. When the brightest stars switch on, their radiation and winds erode the cloud and reveal the cluster, which then begins its slow drift apart. A planet born inside a cluster grows up in a crowded neighborhood. For a while, the night sky would be busy, filled with bright peers. If that planet orbits a binary, the crowd is busier still. Yet even in that complexity, there is order. Gravity keeps time. Orbits trace repeatable paths. Seasons return. When the cluster dissolves, the planet's sky quiets. The brightest neighbors move away and the horizon opens. What felt like a city becomes a countryside. Every example folds back into the same idea. The solar system we know is comfortable and familiar, but it is one option among many that the cosmos explores. Worlds can circle two suns and watch twin shadows slide across their ground. Stars can grow up shoulder to shoulder, trading tugs and light in 1,000 close encounters. Loose families can dissolve and feed the disk with single travelers. Ancient swarms can endure and carry the record of early times around the halo. Whole galaxies can enter busy seasons and build clusters by the thousands, then return to quiet. Nurseries can stretch across the sky, their walls lit by the very children they nurtured. When you picture these places, keep the scale gentle. Imagine a horizon with two small suns near each other at dusk. Imagine a sky packed with bright siblings when a cluster is young. Imagine the deep grain of light at the center of a globular and the hush that comes with age. Imagine a galaxy lighting its neighborhoods in a rush, then letting the glow settle. And imagine a broad, dim cloud that looks empty until your eyes adjust, and then you see it is full of seeds. The ordinary can coexist with the strange. Stability does not require sameness. Planets find rhythm under more than one sun. Clusters hold together long enough for stories to begin, then release their cast into the larger stage. Starbursts write quick chapters that still shape the future. Nurseries make more than stars. They make the conditions for worlds and for watchers. The sky holds all these arrangements at once, proof that possibility is wider than habit and that home can be drawn in many patterns of light. Young stars sometimes announce themselves with fine threads of light. As gas falls inward to build the forming star, narrow jets shoot from the poles and pierce the dark around them. They can run for light years, pencil thin against the clouds, and where they strike denser knots, the impact lights up small beacons. In images, the filaments glow in soft pinks and blues. Astronomers call these scenes Herbig-Haro objects. The jets help the newborn regulate its growth by carrying away spin and excess energy so the rest of the material can settle. The display lasts only tens of thousands of years, a brief spark in a long life, yet it marks the moment when a quiet seed becomes a working star. Not every star holds its brightness steady once the true burning begins. Some breathe. Their outer layers swell and relax in a cycle, and the light follows the motion. Cepheid variables are the best known. Their periods are tied to their true luminosities, which makes them dependable distance markers. Watch the time from peak to peak, and you can infer how bright the star really is. Compare that to how bright it appears, and the space between you and the star becomes a number. RR Lyrae stars play a similar role on a smaller scale, with quicker beats that help map the shape of our galaxy. To the eye, these stars simply seem to flicker, but under a careful gaze, the pattern is precise. They turn starlight into a clock, and the clock into a ruler. Color hints at temperature. On Earth, a blue flame feels intense, often a few thousand degrees. A white star, such as Sirius A, radiates from a surface near 10,000 Kelvin, hotter than our hottest torch. The light spills across a broad range of wavelengths, so it looks ice white or slightly blue to us. Such stars are usually more massive and younger than the Sunday. They burn hydrogen quickly and shine brilliantly, then move on to later stages sooner than cooler stars do. When a white star stands high on a winter night, remember that what looks cold is in fact ferociously hot, a fusion furnace so powerful that the word flame seems small beside it. At the other end of the thermometer sit red supergiants. Their surfaces are cooled by stellar standards, roughly 3,000 to 3,500 Kelvin, cooler than the sun's near 5,800. They compensate with size. In late life, a massive star swells to hundreds of times the sun's radius, and in some cases, even more. If a red supergiant like Betelgeuse were placed where our sun is, its outer atmosphere would stretch past the orbit of Mars and press toward Jupiter. The glow we see is gentle red, but the interior is racing through the last steps of fusion that set up the endgame. The softness on the surface and the urgency inside make a striking pair. These stars stand at the threshold of change. Between the hot white and the cool red are the steady yellows. Our sun is a G-type main sequence star, a middleweight that burns hydrogen at a measured pace. There is nothing rare about that class, and that ordinariness is a gift. The sun is massive enough to sustain fusion for billions of years, yet not so massive that it burns out quickly or tears its system with extremes. Its light is stable, its warmth reliable. Billions of similar stars fill the Milky Way. If life has taken hold elsewhere, it may sit under a sky that feels familiar. The reassurance lies in the average. A calm middle ground can be the perfect place for complexity to grow. Far more common than the bright showpieces are the small crimson embers. Red dwarfs are the most numerous stars in the universe, likely 3/4 of the population in our galaxy. They are cool and dim, so dim that none are visible to the naked eye from Earth, yet their quiet numbers dominate the census. Because they mix their fuel efficiently and sip it slowly, they can shine for trillions of years. That is longer than the universe has existed so far, which means not a single red dwarf has yet lived out its full life. Their long, steady output makes them intriguing hosts for planets, though their flares and close inhabitable zones pose challenges that worlds must solve. Even so, their longevity gives time room to work. If the far future sky is lit at all, it will be lit mostly by these patient lamps. Step back through these examples, and a pattern emerges. Formation begins with gravity, and gravity demands a way to shed, spin, and heat. Jets provide that path for the youngest stars. painting the clouds with fine strokes as they do. Once the core settles into sustained fusion, some stars breathe with a rhythm that turns into a tool. Cepheids and RR Lyrae transform their pulses into distances and maps. In color and temperature, the family spreads wide. White stars blaze with short lives and strong light. Red supergiants cool at the surface and swell while their cores race toward a decision. Yellow stars like ours keep a long, even pace. Red dwarfs carry the majority of the load quietly and for ages beyond easy comprehension. Each type plays a role in shaping the galaxy. Hot white stars flood nearby space with radiation and winds, sculpting their surroundings and setting the stage for later generations. Red supergiants prepare the way for supernovae that return heavy elements to the interstellar medium. Yellow stars keep conditions steady long enough for worlds to form and weather to learn its cycles. Red dwarfs offer continuity, the background hum that will last when other notes have faded. Even their limitations become part of the larger composition. A variable star's instability becomes a measuring stick. A newborn's jets become a carve and a clearing. A small star's simplicity becomes endurance. If you picture these stars side by side, the sky turns from a flat field into a living gallery. Here, a newborn with pencil-thin jets whispering from its poles. There, a clock star with a heartbeat you can count. Over to the east, a white beacon that looks icy but burns hotter than any earthly flame. High to the south, a red supergiant that looks soft yet holds a fierce interior. Near the center, a modest yellow sun that keeps good time and minds its garden. Everywhere, faint red embers that will outlast them all. The diversity is wide, but the thread that ties them is simple. Gravity gathers, fusion lights, time does the rest. Hold that thread lightly. The details are meticulous, yet the feeling can stay soft. Young stars sketch their presence in jets. Some older stars mark distance in pulses. White stars out the it are fiercest fires. Red supergiants trade warmth for size and step toward their finales. Yellow suns keep watch with long patience. Red dwarfs fill the ledger and promise a future that stretches far past our own. In all of it, the cosmos shows a preference for variety within order. The lights above you are not a single kind of thing. They are a family of related lives, each with its own way of shining, each contributing to a sky that is abundant enough to learn by and calm enough to sleep under. Blue giants are rare because their lives are brief. They begin with dozens of times the sun's mass, ignite at extreme temperatures, and spend their fuel at a furious pace. For a few million years, they blaze with icy blue light, bright enough to be seen across great distances. Their radiation pushes on the gas around them and carves out glowing cavities. Entire clouds become H2 regions under their influence, shells lit by ultraviolet light that our eyes do not see directly, but whose effects are visible in soft reds and pinks. Then the giants vanish, their cores collapsing, and their outer layers flying outward in explosions that reshape their neighborhoods. To catch one in the act is to see a transient chapter, a rare page in a very long book. The sky we see with our eyes is only part of the story. A star's color carries more information than a simple shade. Starlight spreads across a spectrum from deep infrared through the visible and into ultraviolet, with each star's blend set by its surface temperature. To our vision, many stars look white, bluish white, or warm yellow, but instruments reveal subtler hues and wide bands our eyes cannot detect. When astronomers pass starlight through a prism or a grating, it unwraps into a rainbow crossed by fine dark lines. That method, spectroscopy, turns color into a language. From it, we learn temperature, composition, motion along our line of sight, and sometimes even a star's rotation. The night is far more colorful than it appears from the yard. Color is also a thermometer. The peak of a star's emission shifts with temperature in a way described by Wien's law. Hotter stars peak at shorter wavelengths and so look bluer. Cooler stars peak at longer wavelengths and look redder. Blue giants can have surface temperatures of tens of thousands of Kelvin. Red dwarfs sit near 3,000. The sun falls in between. Filters on a telescope measure the balance of light in two or more bands and translate that balance into temperature and other properties. A faint red spark, a sharp white point, a pale amber glow. Each is a reading on a cosmic scale. At the opposite end of the life pace, from blue giants are the smallest stars. Low-mass stars sip hydrogen slowly and mix their interiors well, which lets them use more of their fuel. Their temperatures are low compared to bigger stars, so their light is dim. They can be invisible to the unaided eye, even when they are relatively nearby. Their reward for this thrift is time. They can shine for trillions of years. None has yet reached old age because the universe itself is younger than their full natural span. When their long middle chapter ends, they do not go out with spectacle. They fade into white dwarfs and cool. They are quiet guardians of time that outlast the noise of brighter neighbors. Between these extremes lies the work of building matter. The young universe held mostly hydrogen and helium with a trace of lithium. Heavier elements came later. In the cores of stars, fusion joins light nuclei into heavier ones, and each step releases energy. If the product is lighter than iron, carbon and oxygen are forged in helium-burning stages. Neon, magnesium, and silicon appear in later burning shells in massive stars. When such stars die, the collapse and explosion make iron and spread the products outward. Events beyond a single star, including supernovae and collisions of neutron stars, build still heavier elements and throw them into space. The oxygen in your breath and the carbon in your cells pass through these furnaces. Rocks, oceans, and bones bear the marks of ancient stars. Sometimes, a star meets gravity in its most concentrated form and survives to tell the tale. If a star skims past a black hole, the difference in pull on its near and far sides can strip away part of its outer layers without tearing it entirely apart. The survivor continues on a stretched orbit, dimmer or unstable, and the encounter may repeat on the next close pass. Astronomers informally call these survivors zombie stars. The name is playful, but the physics is exacting. With each sweep, the black hole feeds a little, while the star loses a little more. Light flickers, spectra change. The system becomes a laboratory where we watch the border between endurance and destruction. On larger scales, gravity moves stars from one home to another. When galaxies approach and interact, tides draw out long streams of stars and gas. Central black holes play a part in this exchange. They tug on passing stars and can capture them into new orbits. A star that once belonged to a small companion galaxy can end up circling deep inside a larger one after a merger. Others are thrown outward into the space between galaxies to travel on their own. The outlines of galaxies change while many of their stars keep shining as if nothing unusual has happened. Structure is not a cage for a star. It is a current that carries it. Hold these scenes together and a pattern appears. The rare bright blue lives that shape their surroundings for a short time. The half-seen colors that instruments turn into temperatures and chemical lists. The slow, steady embers that promise light in ages we cannot imagine. The steady conversion of hydrogen and helium into the elements that make worlds. The near misses around black holes that mark the limits of survival. The exchanges during galactic tides that move suns from one family to another. Each part is different in pace and scale, yet all are linked by the same rules, written in gravity, pressure, and light. If you picture the sky with these layers in mind, familiar stars gain depth. A blue beacon becomes a clock, ticking fast. A faint red point turns into a lamp that will outlast almost everything. A white spark becomes a temperature readout and a list of elements. A warped light curve from a distant nucleus becomes the trace of a star that brushed a black hole and lived. A faint ribbon across the darkness becomes a stream of stars, stolen during a long tidal tug. The variety is wide, but the thread is simple. Stars are not just lights. They are engines, storytellers, and travelers whose colors and paths reveal what they are and where they have been. Some stars do not belong to any city of light at all. During close encounters between galaxies, tides peel streams of stars from their homes and fling a few into the wide dark between clusters. Others are accelerated by the push and pull near central black holes and leave on long, lonely paths. To find one of these intergalactic wanderers is to notice that galaxies are not sealed islands. Gravity trades members, steals a few, and scatters starlight across the spaces between. What we see in the night above us is only a temporary census. Allegiance shifts when deeper currents pull. The traffic flows inward as well as outward. Dense star clusters that orbit near a galactic center can slowly sink as they lose energy to the surrounding sea of stars. Over billions of years, a cluster spirals down, its members stretched by tides, some folded into new orbits in the bulge, others drawn ever closer to the central black hole. A few are swallowed whole. Many are stripped and left as long streams that wind through the core. In this way, a black hole grows not only by occasional meals, but through slow, steady feasts. The oldest stars that survive the migration give galactic centers their antique glow. Picture a whole cluster settling toward the middle, its brightness spreading out, while a dark engine at the heart gains mass grain by grain. Destructive, yes, but also part of how a galaxy reshapes itself. When a single star strays too near the event horizon, the encounter writes its own luminous script. Tidal forces pull harder on the near side than the far side, and the star is drawn into a long curve of gas. Instead of falling in at once, its matter becomes a bright stream that loops around and gathers into a hot disk. The temperatures in that disk climb to millions of degrees, and the light can rise so high that, for months or even years, the host galaxy briefly wears a new beacon. From far away, we see a sudden flare that fades slowly, and by tracking that fade, we learn the mass of the black hole and the rate at which the gas is being eaten. Each torn star becomes a clean demonstration that gravity can unravel a sun thread by thread. Black holes do not only darken their surroundings. As matter falls in, some of it is redirected into narrow jets that shoot outward at high speeds. Where those jets strike clouds, they compress the gas. Compressed gas cools, and if conditions are right, it begins to collapse under its own weight. Fresh stars follow. In other regions, the same jets stir and heat the medium and slow star birth instead. Either way, the influence runs far beyond the central lightless sphere. Astronomers map long filaments and glowing knots tens of thousands of light years from a nucleus and see the imprint of the central engine written across an entire galaxy. The darkest object becomes a regulator of light, sometimes dimming the room, sometimes pressing the switch that starts new lamps. Not every star that approaches a black hole is doomed. Some find wide, stable orbits and circle for many revolutions, pulled hard but never too close. In our own Milky Way, careful observations have traced the paths of stars that loop around Sagittarius A*, the supermassive black hole at the center. One famous example, S2, sweeps into a tight pericenter and then races outward again, completing its ellipse in about 16 years. Its speed, near closest approach, reaches thousands of kilometers per second. Others, like S4711, run even tighter and faster. The bending of their paths and the way their light shifts in color as they speed and slow confirm the predictions of general relativity in the strong gravity of the inner parsec. Watching them is like watching pure gravity draw letters in space. Stars do not build their households alone. When they are young, they are often encircled by broad, thin disks of gas and dust. Gravity and collisions in these disks gather grains into pebbles, pebbles into rocks, and rocks into planet cores. The growing bodies clear lanes as they orbit, leaving dark rings that telescopes can now resolve. In a few cases, we have even seen hot protoplanets directly as they sculpt their neighborhoods. Our own solar system began in such a disk. The planets and moons that feel familiar under our feet began as dust that stuck, spun, and settled, all under the soft lantern of a sun that was still learning its balance. Massive stars do not just sit in their disks. They affect their neighborhoods on scales that dwarf any family of planets. Their radiation and winds push outward so forcefully that the surrounding gas hollows into bubbles. The edges shine where atoms are ionized and then recombine, giving nebulae their soft, colored rims. One giant can blow a cavity dozens of light years across. A group of giants can merge their bubbles into superbubbles that lace a spiral arm. The shells reshape entire regions by sweeping gas into ridges that later become the cradles of new clusters. From Earth, these sculptures look like luminous balloons and rippled walls. Their beauty is not an accident. It is the signature of power written into the medium between stars. Sometimes a star's light changes, not because the star is breathing or failing, but because its view is briefly hidden. Dust drifting near a star can pass in front and dim the beam we see. The pattern can be regular if a ring of debris is inclined just right, or irregular if clumps and arcs pass at odd times. One famous example, often called Tabby's star, showed deep, uneven dips that puzzled astronomers for years. Careful studies pointed toward fine dust as the likely cause. The lesson is humble and practical. Space is not empty. It is full of material that can scatter, absorb, and color the light on its way to us. If someone far away watched the sun through the dense plane of our own system, they might see similar flickers as comets and dust clouds wandered by. All of these scenes share the same quiet rules. Gravity moves stars from one home to another, strips clusters and feeds black holes, and sets wide ellipses for those that remain. Tides can unspool a sun and turn it into a shining loop. Energy falling in can launch jets that, paradoxically, help new stars begin. Disks cradle the seeds of planets. Giant stars carve cavities and set the next generation in motion. Dust in the foreground writes its own commas into the sentences of starlight. The picture that emerges is not a tidy still life. It is a living system where destruction and creation trade places, where darkness can midwife light, and where the path of a single photon can carry the shape of a whole galaxy's history. Light is not only something to see, it is something that sculpts. In places like the Orion Nebula, a handful of young, very hot stars pour out ultraviolet radiation that strips electrons from surrounding gas. The fog becomes a glowing sea, its edges bright, where atoms capture electrons again and release soft colors. That same flood of energy pushes outward, clearing pockets and corridors, teasing delicate filaments out of the cloud. The cradle that made the stars is also thinned and scattered by them. Close to the cluster, fresh star birth slows because the raw material has been warmed and swept aside. Creation and erosion arrive together, and light itself becomes a quiet force that shapes the rooms of a galaxy. Some stars do their shaping far from any city of light. There are suns that travel alone between galaxies, exiles flung outward during close passes or mergers. A fast encounter near a central black hole can also hurl a star onto a long escape route. These wanderers spend billions of years with no neighbors but the faint haze of the cosmic background. They move at hundreds of kilometers each second, and their light crosses gulfs so wide that it seems almost symbolic. Even so, each carries a story about the violence that sent it away, a message written in motion about tides and encounters and the weight of gravity. While stars travel and carve, they are also busy at their centers. Fusion is the work that keeps a star whole. Gravity squeezes hydrogen until the particles are so close that they merge into helium, and that merger releases energy. The heat pushes outward and balances the inward pull. The balance lasts for ages and makes a star steady enough for worlds to learn their seasons. When we look up at a steady point, we are looking at a furnace that turns mass into light. With a patience No fire on Earth can match. It is no surprise that people dream of copying that process in a reactor. If we learn to bottle a star's method, we will hold a piece of the universe's favorite engine. Hydrogen is where the story begins. It is simple and abundant, and under high pressure, it fuses into helium. As helium accumulates, the core changes, and the star's structure shifts. In heavy stars, temperatures grow so high that fusion continues beyond helium. Carbon appears, then oxygen, then silicon and iron in quickening stages as the end approaches. Not every star climbs that whole ladder, but all contribute. They enrich the space around them when winds carry material away, or when death finally arrives and flings the interior outward. The air you breathe holds oxygen that was made in a star. The carbon in your cells was built in a stellar core, one patient step at a time. That returning of material sets the rhythm for what comes next. A supernova leaves expanding debris that stirs and mixes with the cold medium between stars. A gentler star sheds shells that drift and cool. In time, gravity gathers the mixture into fresh clouds, and dense knots inside those clouds begin to fall inward. New suns ignite, carrying a richer blend than their parents did. Our own system was formed from such recycled matter, with dust that already held iron and silicon and other gifts. In a very distant future, the material we cast off will join another round. The galaxy does not keep still. It inhales and exhales, and each breath changes the chemistry of what follows. Sometimes, that breath becomes a rush. A starburst galaxy is a place and time where the normal pace of star formation quickens to a sprint. Colliding galaxies or close passes funnel gas into dense regions, and whole swaths of cloud collapse together. Clusters ignite by the hundreds. The newborns are bright and hot and loud in radiation. Dust absorbs the light and remits it in infrared, so these galaxies glow warmly in maps that our eyes cannot see. The rush does not last long on cosmic scales. After a few tens or hundreds of millions of years, the fuel thins and the roofs of bubbles blow open. What remains is a galaxy that has been rearranged by its own burst of productivity. Crowded places teach another part of the lesson. Stars are very often born in groups, sometimes only a few at a time, sometimes hundreds together. In a young cluster, neighbors are close enough to tug on each other. Paths twist, partners are traded, and planets must learn to settle into orbits that survive the bustle. Some systems leave the nursery with multiple suns bound for the long term. Others fly apart and drift into the general population. The chemistry in these busy rooms is rich because shocks, radiation, and winds are all stirred together. The chaos is not only noise, it is a way to mix the ingredients that will become later generations of stars and worlds. Even when a star's main fuel is finished, it does not fall silent right away. A star, like the sun, will shed its outer layers and reveal a hot core the size of Earth. We call that remnant a white dwarf. It shines with stored heat, no longer fusing, yet still bright enough to be seen across great distances through a telescope. Cooling is slow for an object so compact and so hot. The universe has not existed long enough for any white dwarf to cool completely and fade into a black dwarf. These faint embers let astronomers measure the ages of clusters and trace the cooling history of a population. They are quiet markers of endings that still give light. Return for a moment to the thought that light changes its surroundings. A handful of massive blue-white stars can ionize entire regions, pulling curtains of gas into waves and leaving hollow bubbles where pressure has swept the dust. The edges glow, and in those edges, gravity sometimes finds a foothold again. Compressed gas can collapse and make new star seeds along the rims that were carved by the last generation. Destruction and creation lean on one another in this way. The same wind that clears can also gather. The same radiation that halts nearby birth can spark it at a little distance. Not every light in a telescope tells a star's private story. Sometimes the beam flickers because of what lies between us and the source. Dust grains, ice, and debris can pass across our line of sight and dim a star in uneven ways. The star called Tabby Star showed irregular dips that did not match the patterns of ordinary variables. Careful work pointed toward clouds of fine dust as a likely cause. If someone far away watched our sun through the plane of our own system, they might see similar quirks when a swarm of fragments drifted past. The path matters as much as the lamp. Taken together, these scenes are one fabric. Young giants turn clouds into glowing caverns, and their light both stops and starts future birth. A few stars are cast out into the deep and carry news of the tides that expelled them. Fusion at the center of each sun binds gravity and heat into a long truce and builds the elements of rocks and oceans and life. The ashes of today become the seeds of tomorrow. Whole galaxies sometimes sprint through a hectic season, then calm and carry the stamp of what happened. Crowded nurseries tangle and churn, then release their members into the disk. Old embers cool so slowly that they become clocks. In each case, the tone is the same. Nothing in the sky is truly solitary, and nothing is truly static. Light sculpts, matter circulates, and time moves through it all, like a tide that you can hear if you sit still and listen. A white dwarf looks like a quiet ember at the end of a long fire. The furnace has gone still, yet the core remains hot and compact, shining with stored heat as it slowly cools. To glimpse one is to see both closure and endurance at once. A star's afterlife, held to the size of a planet and glowing patiently through ages that outlast empires and languages. The light is faint but honest. It is the record of everything that came before. Many stars spend their earliest and oldest days in crowded company. Globular clusters hang around galaxies like beadwork, round swarms that pack hundreds of thousands and sometimes millions of suns into a space that a single spiral arm would barely notice. They are ancient by any measure. Their brightest blue youngsters burned out eons ago, leaving a population of long-lived red dwarfs, warm red giants, and compact remnants that together create a grainy, luminous heart. Inside such a cluster, the horizon would be heavy with starlight. Night would never be truly dark. Everywhere you looked, new points would prick the sky, some close enough to show color, others blended into a milky glow. Astronomers read these communities like time capsules. The chemistry of their stars, the shapes of their orbits, the way their cores are packed, all preserve clues about the early days of galaxy building and the limits of gravity's patience. Crowding does not always mean calm. In a dense cluster, close passes and three-body tugs are common. A single supernova can upset the balance of a small neighborhood. When the geometry turns just so, a star can be slung outward at high speed and sent away from its birthplace. These runaways cross the galaxy on lonely tracks, hundreds of kilometers each second, their motion pointing back toward the commotion that threw them. Some wear that story in their spectra, in the youth of their surfaces compared to their surroundings, in the shock fronts that form where their winds meet the medium they plow through. To find one is to catch a brief note from a noisy childhood that has already fallen quiet. The center of our own galaxy offers a different kind of crowd. Buried behind curtains of dust sits Sagittarius A*, a supermassive black hole with about 4 million solar masses. Around it, a handful of stars draw long ellipses that astronomers have traced for decades. One, labeled S2, dives inward every 16 years to a distance measured in light hours, and then slings back out, reaching speeds of many thousands of kilometers per second near its closest approach. Others weave even tighter paths. As they rush, their light shifts in color, and their timing matches the curves that Einstein's theory laid out. We cannot see the black hole itself, yet the choreography of these stars writes its signature in the open. They are dancers skimming the rim of a deep well and returning, proof that not every neighbor of a black hole is a victim. Some endure and trace out a map of space-time each time they complete a circuit. Gravity around such a mass does more than hold a star to its route. It bends the route itself. Orbits that would be simple if space were flat become subtly twisted when space is curved. A star that would close neatly on itself instead returns to a point a little ahead, drawing a rosette over time. Farther out, the effect is gentle. Closer in, it becomes dramatic, and the speeds approach 1/10 of the speed of light. In other galaxies, where the center is too distant to resolve, the same physics reveals itself in the swirl of whole nuclear star clusters. Warped paths are a fingerprint. By reading them, we weigh what cannot be seen. Step back from the center to the wider neighborhood, and the distances grow quickly. The nearest star beyond the sun sits a little more than 4 light-years away, which is about 40 trillion kilometers. Numbers like that are easy to say and hard to feel. If a craft left Earth with the pace of our fastest deep space probe, the voyage would last tens of thousands of years. Yet Proxima Centauri is still our closest neighbor, and it already carries at least one small planet in a zone where liquid water could exist if conditions are right. The gap between close and far, between ordinary and extraordinary, is the space that starlight crosses every night to reach us. That gap keeps the sun precious without making it unique. Scale widens again when you consider how many stars share our galaxy. The Milky Way holds hundreds of billions of suns. Most are small and quiet. A modest number are large and brief, burning blue and shaping their regions with light and wind. Some live double or triple lives. Some carry families of planets. From a rural hillside on a moonless night, we see only a thin sample, a few thousand points. and a pale band arcing overhead. That band is our disk, seen from the inside, the combined glow of countless distant stars, blurred together by distance and dust. To imagine the Milky Way in full is to picture a wheel more than 100,000 light years wide, and then to place our sun as one grain within that sweep, not at the center, not at the edge, but somewhere comfortable in between. The stars you can name with the naked eye are almost all members of that same wheel. Orion's belt, the Pleiades, the bright eyes of the Big Dipper, the summer triangle when the warm months return. Each is local in the galactic sense. The true outsiders are few. In very dark skies, the Andromeda Galaxy is a faint smear that reveals itself only after your gaze has settled. A couple of other subtle smudges belong to small neighbors of our own. Everything else is home. That is why the Milky Way itself, when it lifts like a river of frost across the sky, feels both familiar and impossible. You are seeing down the length of the street you live on, and at the same time you are looking at a city so large that its lights blend into a single seam. All of these scenes connect. A white dwarf cools in the corner of a cluster whose oldest members were born when the galaxy was young. A runaway star slips past the outskirts and keeps going, still warm from the push that exiled it. Near the center, bright companions of a hidden mass sketch their orbits while gravity curves the lines they draw. Beyond our yard, Proxima sits across a gulf so wide that light must commit years to cross it, and yet it is close enough that its planet already pulls our attention. Around us, hundreds of billions of other suns keep their own schedules, most unseen, all contributing to the faint band that lifts on clear nights. If you let the whole picture settle, the feeling is not of noise, but of a patient system working at many scales. Nothing is truly alone. Nothing is truly still. The galaxy hums, from its glowing swarms to its quiet embers, and you are lying under one small patch of that gentle, endless choir. What looks like a private ceiling of twinkling points is really the thin slice of a great rotating disk. On a dark night, your eyes cut across the Milky Way's plain, through lanes of dust and fields of stars that share a long orbit around a common center. Realizing this does not diminish the comfort of the view. It deepens it. The sky is not random decoration. It is a window into the neighborhood we live in, and every bright dot is a neighbor keeping its own steady time. Gravity keeps this city of light in motion, and sometimes it loosens the bonds. When galaxies brush past or fold together, tides pull long ribbons of stars from their spirals and toss a few out into the wide in-between. Encounters near central black holes can fling others on escape paths. These exiles drift for billions of years with no galaxy to call home, their light crossing gulfs where nothing else waits to greet it. A few may carry planets with them, small families traveling together through thin dark. To find one is to learn again that galaxies are not quiet islands, but living structures. The ties that hold can be stretched and, on rare occasions, broken. Endings write their own script in the thin material between stars. For suns like ours, the late chapters are gentle and luminous. As the core changes, the outer layers expand and loosen. Gas peels away in shells that drift and arrange themselves into glowing rings and arcs lit by the hot remnant. in the center. We call these shapes planetary nebulae, an old name that stuck long after the misunderstanding faded. They are not worlds, they are signatures of a passing. Each one paints the sky for tens of thousands of years, then thins and blends into the interstellar medium. The beauty is brief, the influence lasting. The shells carry carbon, nitrogen, oxygen, and other elements outward, adding to the stock that will be used again. At the heart of such a scene rests a white dwarf. It is the core left behind, dense and small, the size of Earth and yet nearly as heavy as the Sunday. Fusion has ended, but heat remains, and that heat leaks away slowly as a soft, steady glow. Matter there is pressed into a state that resists further collapse by quantum rules rather than by ordinary gas pressure. A spoonful would weigh tons on Earth because the atoms are squeezed so close that the spaces between vanish. Over billions of years, the ember cools. In theory, it will one day become a black dwarf, a cold, dark relic. The universe is not old enough for any to exist yet. For now, white dwarfs serve as fossils that help date clusters and trace the cooling history of our galaxy. Not every finale is this quiet. Some stars are massive enough to race through their fuel and reach a core that can no longer support itself. Gravity takes over. The core collapses in a breath, and the outer layers rush inward, rebound, and fly outward. For a short time, the explosion can rival the brightness of a whole galaxy. Shock waves create and scatter heavy elements, and what remains at the center becomes a neutron star, or, if the mass is great enough, a black hole. The contrast with the gentle fade of small stars is stark, but the outcome rhymes with the quieter story. Material returns to the medium. The next set of clouds inherit the enrichment. New stars begin with more tools on their shelves. Hold the two endings side by side, and you can feel the pattern. A small star spends a long life in balance, then sheds and rests. A large star lives fast, ends loud, and leaves an extreme remnant. Both endings matter for what follows. Both write to the same ledger of elements. Both keep the galaxy active by feeding it with what otherwise would have remained locked inside a single sun. The sky changes on slower scales too, and that change is easy to forget from one evening to the next. Constellations feel fixed because a human lifetime is short compared to a star's crossing of its local patch. Give the scene time, and the patterns warp. Clusters swell and fade as their members drift apart. Spiral arms gather and thin. Entire galaxies meet and exchange material. Rogue stars slip into the void, and others are drawn from it back into crowded lanes. Even our sun is temporary, one of hundreds of billions in the Milky Way, a steady middleweight that will one day trade its current face for a giant's glow and later for a white dwarf's small light. To feel this movement is not to lose the stillness that helps you rest. It is to let the mind float with the long tide. The Orion Nebula lights because its young stars flood their nursery with radiation. Elsewhere, a cluster holds itself together for billions of years, dense enough to keep a bright core while the outskirts shed members into the disk. In the deep center of the Milky Way, stars like S2 carve narrow ellipses that trace the gravity of an unseen mass. Far outside the bright regions, a handful of exiles move through clean dark, patient as stones rolling on a riverbed. All of these scenes are variations in the same composition. The subject is transformation. Think again about distance and number. The nearest star beyond the sun sits a little over 4 light years away. Light takes years to cross that gap, and a fast probe would need many human ages. Yet, that neighbor is close compared to most of what we see. The faint band that lifts across the sky on clear nights is the glow of our disk, seen from within, the blended light of countless suns, blurred by dust and distance. Almost every point you can name belongs to this same home. Only a few pale smudges, like the Andromeda galaxy under very dark skies, come from outside. Our view is a tiny slice of a vast system, and still, it is more than enough to carry the feeling of scale. The more you learn about how stars end, the more the present light gains meaning. A planetary nebula is not just decoration, it is a memoir written in gas. A white dwarf is not just a faint point. It is a durable record of a life that shaped the neighborhood. A supernova remnant is not just a tangled ribbon. It is a workshop where elements were forged and delivered. A rogue star is not an odd footnote. It is proof that gravity can both gather and release. The fixed and the flowing live together in every view. Let the pieces fold into each other. The disk you look through at night is alive with births and endings you cannot see in a single glance. In one direction, a cluster is dissolving, its former members joining the general traffic of the spiral arm. In another, shells from a dying sun are glowing for a short season before they thin into the background. Farther out, a shock front from a recent explosion presses on a cloud and seeds the next round of collapse. Somewhere a small star sips fuel and barely changes across the entire history of humanity. Somewhere else, a very massive star is already preparing to fall in on itself and write a sudden bright line into the record. If you could linger in one place long enough, the changes would be obvious. Constellations would lose their familiar angles. New figures would appear. The band of the Milky Way would tilt and thicken as our position shifted. In the cores of galaxies, orbits would precess and tell you that space is curved. In the outskirts, dim streams would reveal where smaller companions were torn apart and folded into a larger whole. The universe keeps time at many tempos. Some you can hear in a single lifetime. Most you sense only by listening for the pattern and letting the knowledge sit quietly. The lesson is simple and generous. Stars do not just decorate the night. They build the material of worlds. They mark the passage of eras. They rise in crowds and leave alone. They end quietly or with sudden force, and in ending, they begin again in other forms. The strip of sky you see is both personal and communal, a private window into a public city of light. What you call a constellation is a brief arrangement in a long dance. What you call a star's death is a step in a cycle that refills the shelves from which the next generation will draw. If you let that thought drift through you, the sky becomes easy to rest under. It is vast, but not indifferent. It is moving, but not hurried. And you are looking into the place you belong, a small, steady witness inside a galaxy that keeps changing while it holds. Let the picture of that living sky stay soft at the edges. The disk you belong to is still turning, quiet as a slow tide. Constellations loosen by a breath you cannot feel. Streams of old light glide over you like a pale river. Somewhere a shell of gas is fading, somewhere a small ember is cooling, and the band above carries it all without hurry. You do not have to hold any names now. Let them slip like grains through open fingers. If a distant sun once wrote its story in your bones, it is enough to know that the story keeps going. The room is darker. Your eyes are heavy. Each inhale rises like a small moon. Each exhale settles like dust into the dark. Imagine the last porch light of the day winking out. The stars remain, but they seem further away, gentle and kind. The Milky Way turns, almost silent. Your body finds the same rhythm. Shoulders soften, hands loosen. Thought drifts like a slow boat on a wide, black lake. There is nothing to finish. The galaxy will keep its time. The river of light will keep flowing. You can set your weight down and let the night carry you. Breathe in once more. Breathe out a little longer. Let the sky dim to a whisper and slip into sleep.